Welcome, everybody. We'll be continuing this part 2 of looking at the challenge for task 8 on the Codebreakers NSA 2024 challenge. We left off where we were looking at this possibly ECC function where we were following the private key in a buffer. And we stopped with the last part getting a little bit longer. So we'll continue on and hopefully we'll find something new in this video. So we left off, we had identified these copy functions and we were walking through this private key buffer ostack64 static value function. And if we walk or step into it, we can see that something's going on. We're not really sure what. A lot of math, I guess, is what it kind of looks like. Maybe it's just moving data around. This could be just another copy. Looks like it's doing 4 bytes at a time. This might just be another copy over. We have this function here, times 4, not sure what's going on there. And then some more, but what we could do is we could go at a really low level and analyze every single one of these functions and go assembly line by assembly line, but after scanning through it, it didn't look like anything bad is going to happen, so we could just step through it here. So if we take our context, where are we at? Go to 49.3A4. It looks like we're out there to the second copy, so we can step through. We can identify here that it's going to copy the another 32 bytes, but we already know that's going to happen. Step down to the next function, so we should be here at 93C4, which it appears we are. Nope, 93C4 down here. So if we look at it, it's going to have our public key twice, or not public, private key twice, a buffer to possibly store it, or store something, and then a static value, which appears to be, doesn't appear to dereference it, it just appears to be the actual pointer to the static value. So I'm going to step in it. We could just step over and see what happens, but I kind of want to see what it does with that static value first. I'm just going to follow that real quick. So param4, it looks like it's just being used in this first function, so we can just identify what it looks like. So come down here to this first function, and static should be here. And it looks like it's pointing to these random bytes. It looks like 5.1 is printable, so maybe a string, not a string. But we know we're working with cryptography, and we know that it's something's going on. They're just random bytes, so maybe it doesn't hurt to just Google them. So if we just take this and just search this with ECC, because we know we're using elliptical curve, block. Let's get rid of the 0x. It looks like the values do show up a couple times. So F3, 9, whatever, there's ECC, SECP256, which we are using 256 curve. We could walk into that one. I'm going to click on one that might be, maybe this one will work. Just do a quick jump down to it. So it looks like this might be the value curve N32. 5.1 does the next bytes go 849E. 849E, so it looks like, yep, this appears to be the N curve in memory. So if we go to this address in Ghidra, move this guy over, looks like we're right here, 5.1. I'm going to make a character pointer here. Data, create array, 32 characters in length, I believe. Let me check back here. This will be 8, 16, 24, 32. Say OK. We're going to rename this to N curve 32. Not sure why it's saying question mark. If we do, the data type should be set. Oh, nope, we didn't set it to a character array. We set it to create array. I want to actually make this a, I might even do unsigned char array. There we go. So now it shows up in his array. Since we know this is going to be end curve 32, there's a good chance the other bytes around it are also something. So if we look at all these f's, put this off to the side, a bunch of f's, zeros, and then more f's with a 1 right there. So this looks to be curve at P32. I'm just going to keep it similar to the last one, so P underscore curve 32. Choose the data type. Do unsigned char array of 32 characters. Just clean up the memory a little bit. The one right below it goes 96C2. There's a 96C2 right here. Appears to be 64, so it appears to be the G point. So this would be the public exponent for the curve. This is the best way I'm going to explain it for now. So we have X and Y. So it'd be just 2 points. We could break this up. I'm just going to set it to 64. Choose data type. Actually, nah. I'll set it up to 2 of them. We'll set this to unsigned char 2 with both of them being 32 characters in length. That didn't work the way I wanted it to. Oh well. I was hoping it would break it up so I could split them up, but that's fine. Curve. I'd do X and Y, but whatever. Curve. We'll do G underscore curve 32. And then lastly, 4B60 appears to be this one. So we could set this to be a data type unsigned char 32. And this appears to have cleaned up this entire memory segment. This will be B underscore curve underscore 32. Sweet. So we have a couple function pointers appears down here. The word Falcor. I don't think that relates to anything. We could just do a quick Google search. Falcor. I don't think it's talking about that, but it might be. ECC. Yeah, I'm not seeing anything of use, so it won't be anything. But now we know that some of these data variables are relating to ECC, so we definitely are in the right spot with knowing that these functions have to do with ECC. At this point, we could try to just walk through it and see what they're doing, but that kind of gets gross. So what I like to do is just look up ECC library or something. I'm going to use micro ECC. Micro ECC, I think I want to use micro ECC. Let me check real quick. Check my notes at least. Nope, I don't want to use micro. We could use micro. There's a good chance it'd probably be the exact same. Looks a little bit more. It's going to look the same no matter what. I'm actually going to go to a library called Nano ECC. A lot of what I like to do is go to these libraries that are designed for low-level electronics, because we know this is going to be running on a Raspberry Pi, so it might be using this library. So if we looked at ECC.c, we can see that our curves are defined. Appears to be a lot more curves in this, so this happens to have from curve 16 all the way to 48. We only really care about 32, but the fact that these are kind of set up similarly right after each other, maybe they took this library and just gutted it. So it doesn't hurt for us to just pull this guy down. Copy this, come over to our, not that directory. Not sure if we need that directory anymore. Just do a git clone. I'm going to make a directory called code, because in this challenge we're going to be start coding again. Git clone this library. We can change into nano cc, start looking at the code, see what's actually happening, because maybe we can find or identify something that looks familiar between these two functions. We have an ECDSA verify, ECDSA sign, VLI mod multiply, ECC valid public key. Well, maybe it cares about this. Maybe it's verifying a public key of some sort. It's probably not making a key. It probably already has a key made. ECC point multiply, XYCZ. In this, I'm not really going to, at the moment, I'm not going to dive into how ECC works. I'm going to just start on reversing first, and then we can dive into the how ECC kind of works at a high level, or the level we need for this challenge at least. So with that, we know that the curve n is being used here, so we could probably follow the curve at the beginning, see if it gets used anywhere. Curve n, if I remember correctly, the library likes to just identify what curve you're using and just store it. So we're actually going to be using this curve underscore n down here. Curve n is used in a compare in the make key. We don't care about make key. It's used in sign in another compare. It's also used in a sub as the third parameter, which it happens to be used in the third parameter here. Compare, mod multiply, it's used as the fourth parameter. Add, it's used as the fourth. Multiplicative inverse, it's used as the third. So this would be 1 divided by k. But none of these functions are really lining up. So what I'm kind of identifying is if a function is using n, is there another only 2 functions beneath it, and that might be it. In this library, I'm not really identifying any. This could just be that they modified the functionality severely, but I'm hesitant to just jump in and say that it's directly this function and then modified. What I'm going to do is take GDB and actually finish this function and see what our output is. I'm going to scroll up right here and identify what I think will be where it's stored, because I think it's going to be stored just right in the same same spot, because I think it's going to be like a store location, a value that we're going to actually modify, and then our n curve. Oh, wait, this is actually the wrong function. I'm going to scroll up to where we jumped in, which should be at AC40. AC40, you go quite a ways. AC50, 840 should be right here. Oh, 40. So this is where we're coming in. So it's this address. It happens to be the exact same one, but I just want to make sure. We can finish. We can check this value out now. We only care about the 16 bytes actually. So it looks very different. We know that it's using the n curve of somehow. So maybe it's probably not doing modulus. We could check to see whether it's doing we knew the starting value was CC's, I believe. Nope, it's all B's. All B's should be 0x62. Is it 62? It's 40. No, 63. Lowercase b's at least. So if we take this address and just print out the value at this minus 0x C3, or 63. 1, 2, 3, 4, 5, 6, 7, 8. We can see we have this 9C, 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 FB, C2, 2450, which right now doesn't really line up with our curves at all. I don't think I have any. Oh, this one should. If we check our curves, we know we were working with the n curve, so we're going to just go straight to that one. Curve n doesn't really line up with this curve at all. It should be 50. Oh, it actually looks very close. It appears to be off by 1 byte though, so maybe I might be just off. Yeah, it should actually be C62. That should be all B's. C3 are C's. Now if we do 512563 FC, appears we're falling off right here though. I'm not seeing 9D's anywhere else in here. There's some FFs. We could continue checking the rest of the bytes, which might not hurt. Oh, it appears to be just grabbing the first 4 bytes anyway. So let's actually make this a long pointer. There we go. FC, C2, CA. So it seems to be lining up with all of n. So it looks like it's just taking our private key plusing n, which if we looked at the code here, we didn't identify anything that actually did an add except for this one down here. We do an add right here with our p hash with an ECDSA sign. So it actually doesn't appear to be correct for that or any of these functions. So we're just going to say this is private key plus n. We're not really sure what it's doing with that, but maybe it doesn't appear to be standard within normal cryptography, or at least in the library we're looking at, so maybe that's something. So we'll just continue on for now. Looks like we have a function that just returns a function pointer. We could look at this function and see that we're doing a read from urandom. So it looks like this is just going to be getting random bytes of some length. So I'm going to call this random bytes pointer. It's not a pointer to random bytes, but it's a pointer to a function for random bytes. If we follow lvar4, we should come down to this function, which uses another pointer. Actually, follow this one first. Looks like it's doing some. I'm going to make this larger. Doing some kind of memory movement of some sort. Not really sure what's going on. Check out this pointer. Looks like it's another. Looks like there appears to be two in memory that are the exact same function. So this might actually just be another pointer or the same pointer. Random bytes function. So a pointer to random bytes function that works. It checks to see if it's undefined again, and it actually calls it. ivar1 appears to be set from param3. Param3 is probably the static again, because that's how it appeared to have been used recently. Looks like it should be 0x20. So that's, oh, yep, nope, 0x8. So that should be 8, I believe. Here it's also using static value plus 4, which should be curve P. So it's also using curve B. So random bytes and curve P just for now. With that, we could probably go back to our source code and see if there's anything that uses that similar value. I'm just going to search random. It appears that make key might use random. It looks like it's taking a set, or it's setting the private key to random, which makes sense when you're creating. Shared secret also appears to be using a random key. Passes it into ECC point multiply. Looks like ECDSA sign uses a random key, but none of them appear to be using the curve P yet. So we could also just identify the curve P. I think it's curve underscore P, see where that's used. Curve P is used within ECDSA verify. I think that's still verify. Multiplicative inverse verify, curve P. Curve P, curve P, curve P. What's this function? Appears to be doing something in memory. Mod fast, that doesn't matter too much. I don't think, because it didn't look like we had all that memory move, or we didn't have that much memory movement at least. Could be wrong. Compare. Multiplicative inverse fast uses it. ECC double Jacobian point uses it. Uses it a lot, but doesn't appear to be used that much. So if we look back at Ghidra, curve P should be parameter 2. We know it's curve P because if we go to static values, not static values, P underscore curve 32 in memory, it's going to be using this address plus 4, so plus 4 bytes. It's going to be curve P, so we know that. Following curve P uses it once in the first function, which might be removing it in memory, but it doesn't appear to be doing that. So it looks like it's doing something with the size. Maybe it's modifying curve P itself. For that, doesn't appear to be, oh, yep, it's dereferencing it right there. It looks like just to be increasing values though. So maybe it's identifying a certain value of curve P. We can step through because this should always be the exact same as long as it's not modifying curve P in memory, which I think curve P might be in static memory. Is there an easy way to identify whether this is static or writable without going to the top? I want to say this is some read-only data versus, well, the sections are not making sense. Read-only data versus T data, I guess. There's no BS. Oh, there's data. These are a lot more pointers. Oh, we're also, whatever. P underscore curve. I'm going to assume that it's in read-only data right now. Oh, right there. Yep, read-only. It's at the very beginning. Should have scrolled a little bit. So curve P is in read-only, so it's not being modified. So this should always return the same value, whatever it is. It also gets used down here with this IVAR, which appears to be checking to see if it's equal to 0, which when it does that, it might be like greatest common denominator type stuff. Param1's also used, param1 we don't care about, curve B. Curve P we care about. It's doing some kind of loop. Oh, it's doing a comparison. So maybe this is like a greatest common denominator divisor, kind of checking to see if they're co-prime with each other. We'll keep stepping through looking for curve P stuff. So it looks like there's a check for valid public key curve P with the public key. This could be something. I was hoping to use a curve P with random bytes at some point, but maybe it's not, or I'm just not or I missed it. I'm not going to go through the whole list again. With that, we could just skip over it since we know it's been using random bytes and a curve P. So maybe it's just grabbing random bytes and making sure random bytes is co-prime to curve P. That's very common within cryptography systems to make sure you have unique values. Don't need that one. I want this one. Where are we at? We were just actually looking at these these functions. So we know we're using random bytes. Random bytes with curve P is being used there. We can check out this function, which appears to use our buffer. The local 98 pointer, which is equal to 0, which is either our private key or the private key identified with private key plus n, just based on this. So there's some kind of check to see uvar2 is valid at some point. pvar5 appears to be the inverse of this, or maybe it's the same. It's not 0 because this one shouldn't ever happen if we're working correctly. Oh, maybe it could be 0. If it's not 0, it would be set to local 98 at uvar2, which is be the same as this random curve. So maybe it's our random bytes, or P itself. Let's say random or P. We could step through and find that out. Looks like we're going to use static value plus 2, what should be 0, 0, I think, plus 1. Oh, no, it's treating it as a short. Since it's a short, it would actually be, if we go to P curve, it should be right there. Since it's a short, it'll be the second set. So 0x 100 plus 1, so 101, it looks like. We're going to step through that just to make sure it all lines up. We're going to just jump straight to there. We don't care too much about what the random bytes and P curve functions are returning or setting, because there's a good chance they're just random bytes. Step through this. Need to grab the right one. I don't need this one anymore. Let's just look at the public key. I want to keep this one. Don't go break at this address. Continue. So it looks like we have we look back, we have buffer beginning, so those both should be the same. We have local var 98, whatever that's set to. This B3 appears to be our, I think if we do search for the print, not that address. Let's do this address. Yeah, so that's going to be n. So it looks like this value is going to be our n plus, private plus n, whatever happened there. This one appears to be our random bytes, I would think. Doesn't look like the P curve. Oh, don't need that many bytes. 16 bytes. DE2D66E4. That doesn't appear to be our random bytes at all. And it doesn't appear to be the P curve either. Or it doesn't appear to be the P curve. It just appears to be random bytes. Maybe the P curve did something to the random bytes. But since this should just be, if we look it up what the P curve is, P curve ECC, it should be a large number. We'll actually just open this one up. Curve P. So it just said applications to cryptography. Oh, that's just curve P ECC. Like, what's it? I just want to. Oh, we can actually look up P256 because that's the version we're using. That's not what we want. We saw the word ECC P2. I know we're using 256 based on the key. We saw a specific name when we searched the curve last time, though. Do I still have that one open? I think if I go back, it should come up. Oh, right here. We saw this word, SEC P256R1. Let's look that one up. Elliptical curve. So my understanding is that the SEC is just a standardization curves. Cryptography or ECC can use any kind of curve it wants, really. It just depends on the points. But these are just statically set points within a or identified system by NIST. If I think I go to NIST, it might show. Nope. Okay. The NSA came up with these curves, so maybe there's a reason we're using that within this challenge. Generator point order n. See, these are the numbers not in hex. P should just be a large, I think the largest number possible. That's why it's all F's. I think it's the largest, one of the largest primes within this curve. We could do a quick search and say NIST standards. See if that shows up. Oh, this is actually by NIST themselves. Oh, do they have the curves in here? Not seeing them. I was hoping there was a public comments. Probably isn't what we want. Doesn't matter too much, but the P curve appears to, or should be, something that's identified as a large prime. So when you get a random key pair, we're not really sure what we're doing with our elliptical curve yet because we haven't identified the further functions, but when we step further, I'll come back and identify what it should be identified or used as. So we know we're at this function. We just need to then step into it and identify what kind of variables are set. We have identified that our points, this should be our private key. This is our either out data and in data of some sort. This should be the P or in random, and then that should be our size, 101, as we had identified. So we're going to step in here in Ghidra, see what it identifies as. There's a lot of functions going on, but that kind of makes it easier for us, because we just need to try and find a function that kind of uses the same layout. Even just the parameters might be enough. So if we come over, I'm going to open this to the side. We can start looking at the larger functions. We are going to want to, I'm just going to go into the bottom. I think we'll start scrolling from there. So ECD, there's three kind of main functions within this cryptography library. ECDSA verify, ECDSA sign, VLA mod multiplication, don't think that's one of them. ECDH shared secret, valid public key. I guess there's a couple more than three. Make key we don't care about because we're not making a key as far as we know. ECC point multiply. All these other ones should be helper functions that are used within those. So if we come in, just identify based on this one, it kind of has a similar sort of layout at the beginning, just based on what we're looking at. Based on this for loop, there's a while true loop, but the number of functions isn't really lining up within that loop. There's also a block at the end that's not really lining up. If we scroll up to the top, ECDSA verify kind of has a better layout. Oh wait, we just looked at that one. The for loop didn't line up. Mod multiplication doesn't appear to work. Mod or ECC point multiply kind of actually looks a lot better. So if we look at I'm just looking at the for loop and while true loop, it appears to have three functions within there. That lines up. After the while loop, there's a block of functions which appears to line up correctly too. At the top, it appears this one has three. This one has a couple more. But if we check out this XYZ initial double, CZ initial double, it was right there. It looks like that maybe this one's just statically compiled in that spot, as there's an if statement, and we have a couple more functions that maybe line up. So maybe this is looking very, very good for what we're looking for. So we're going to go back to the ECC multiply. ECC point, should just go down. And we're going to start from maybe the for loop, because that's kind of the spot that's looking the best. We can't just go straight and say this is this function. Let's try and step into the functions and see what they're doing. So let's go to VLI test bit. Ooh, it might take a little bit. Oh, there it is. It looks like it's doing a point divided by 8, anded by 1, shifted left by the point anded again. Which it may be hard to see, but this actually is very similar to that. The point at divided by 8 is very synonymous with anded by kind of the last byte. And then it's taking param1 pvli at pbit shifted left. So this kind of looks very similar to this function. So I'm just going to temporarily name it that, VLI test bit. If we come down to this next function, I need to go back now. If we go to down here to xycz add c, check to see what that is. There appears to be a bunch of functions in here. Cz add c, and just lines up well again that there's a lot of functions. A lot of these appear to be the same function, so is mod set used several times, or mod sub, mod sub, mod sub, mod sub, mod sub, mod sub, and it appears to be lining up with the sequences, so it goes 1, 2 in a row, 2 in a row, 2 in a row. So it looks like we're kind of on the right track. I'm going to make sure, we're going to go to mod sub just to make sure that it actually lines up. I think it should be towards the top. There it is. Mod sub appears to call possibly VLI add within an if statement if borrow is set. So it looks like it's going to call VLI. Oh, did I do mod sub? Is that the one we wanted? I wrote it, so it must be. So it looks like this might be VLI sub. Ghidra didn't identify it as having parameters right away, as it's just going to take the original parameters right off the top. So VLI sub takes a for loop and does a comparison just if it's greater than the left ren or something. So like right here, if it's equal to the comparison. So there's a good chance this is going to be VLI sub. We could just call it ECC sub, anything else, but I'm just going to keep it synonymous with what we're looking at. So this might make this VLI add. VLI add seems to have the similar setup to sub, but I'm guessing that this pluses around here are probably different. So let me go to VLI sub just to check it out. It looks like, yep, there's subtraction instead of addition within. So let's go back. So this is going to be VLI add. So like this would make this VLI mod sub. So we could go through and identify each of these to make sure they all line up, but I'm going to give you a hint and say that they do. What function was I in? Add carry. Just to save some time. So this is going to be XYCZ. Press the wrong button. Rename XYCZ add C. We can come through, name all these real quick. VLI mod square fast. Setup, yep, that lines up. VLI mod multiply fast. VLI mod add. And then down here should be VLI set. Go back to the other function using this. So this one's going to be XYCZ add, not with the C. We can scroll down. Looks like a lot of these functions were named. We can check. So probably the test bit is being done in here. We have an add carry, sub, fast, inverse. Goes right here, VLI, mod inverse. And if you wanted, you could step through all these functions to make sure they line up better. Mod fast, add, apply Z, set. We can come back to the top. This stuff probably has to do with the initial double, and it looks like they're all named anyways. There's a pointer here. We could walk through it and identify where it's actually being called and what the function is, but just to save some time, as this video is already close to 40 minutes long, this is going to be the Jacobian double function. Let's do end of line comment. Jacobian function, apply. That put it way up there for some reason. That's not where I wanted it. Jacobian double. Oh, it might be because of the EOL or the. Put it there, please. It did in the assembly. Oh, post comment. Jacobian function. Apply. Still does it. It's doing the assembly, not the decompile, but that's fine. It doesn't matter too much. As long as we know that right here is where that's happening. We can identify that based on stepping through, and then if you also go to the XYCZ initial double ECC point double Jacobian, and then apply Z above. There's a set, two more sets above it, so it all just lines up. There's one more function we haven't identified yet within an if statement. I think that should just be a set. It might be calling something else. It doesn't, as far as I remember, there's actually nothing there. Looks like it's going to be within the double. Oh, it's probably VLI clear. VLI clear. So all in all, this is a pretty standard looking function of ECC double ECC point multiplication. Multiply. Where are we at with that? Let's go to where it's used, which should be in decrypt question mark. What do we call it? Decrypt question mark. Go back into this function. So ECC point to multiply. If we come down to this next one, we're not sure what's going on here. It looks like it's moving memory around again. So buff out, static, buff bag, static 20 should just be the size 20, the buff beginning. So this might just be mem copying it to our out buffer versus where it was at. So I'm just going to say mem copy question mark. We can step further into it and check it out later. Buff bag and static value are passed into this last one. Looks to be another memory move of some sort. So we'll do a copy. Looks like probably another copy of copy 2 up here. And that appears to be all this function is. So this appears to be our main ECC functions. Yeah, so we just found our ECC functions. I think that's actually a good spot to stop on this part. We haven't gotten to the exploit yet. All we did was walk through and reverse engineer. So far we haven't identified anything wrong with the elliptical curve. Usually the way to identify exploits within elliptical cryptography is identifying what's wrong. The only thing we've identified is this private plus n, which is interesting, but we haven't identified anything with it yet. But with that, I think I'll stop this video and continue on to the next part.